Welcome everybody to this seminar. My name's Professor Peter Taylor. I'm from the University of Leeds and I'm one of the investigators on the EPSRC Network Plus for the decarbonisation of heating and cooling. Now this event is organised by that network as part of a series looking at the different challenges of decarbonising our heating and cooling sectors and behaviours. And this month we're delighted to welcome speakers from both Cardiff and Leeds universities who will present their research on different aspects of sharing heat. And we're very grateful to our presenters for providing their time today. But first of all, what I want to do is to introduce our first set of speakers. So that's Dr. Michael Taylor and Dr. Wu Gao from the School of Engineering at Cardiff University. So Michael is a research associate in the School of Engineering and his research is on integrated energy systems. He looks at how district heating and cooling networks could help decarbonise our energy use, reducing waste and providing demand-side flexibility to the energy system, to the electricity system. And he's over 4 years' experience studying the modelling, optimisation and control of multi-systems. And Dr. Wu Gao is also a research associate in the School of Engineering. His previous research is centred around the study of degradation and stability of municipal waste and coal gasification technology. And both the speakers are currently working on the EPSRC funded project, Integrated Heating and Cooling Networks with Heat Sharing Enabled Smart Prosumers. So with that introduction, I would like to hand over to Mike and Wu.
Okay, thank you very much, Peter. Well done on saying that very awkward title for our project. Usually trip you up. Okay, so today we're going to be talking about balanced heating and cooling networks and the modelling and simulation work which has been carried out as part of an EPSRC project which Peter mentioned. The project began in April 2021 and it's set to run for 4 years. It's a collaboration between Cardiff University and the University of Exeter, and we also have project partners on our advisory board. So we have Kensal Heat Pumps, the University of Warwick, ISACS, DTU and Bridgend County Council. And the project split across 3 main themes, which are integrated network analysis, underground heat resources and policy, which are taken care of by Cardiff for the underground heat and network analysis and Exeter for policy. And there are 3 main objectives across technical, market and policy issues. These are to investigate design and operation of balanced heating and cooling networks and their interface with the electricity system. It's to study potential local heat markets, which are enabled by connecting consumers and producers of heat, and also to understand the challenges transitioning to these new systems in terms of policy and regulation. This slide also just shows the different work packages involved in the project and how they fit together. Wu has already led work package 2 and I've been leading work package 3. The 2 topics that we're going to talk about in this presentation today are coupled thermohydraulic modelling and simulation of a horizontal ground source array. Wu is going to be talking about that, and I'm going to be talking about the above ground equipment for a balanced heating and cooling network. So I will hand you over to Wu.
Thank you, Michael. Thank you for the introduction to our EPSRC project. Hello, everyone. I hope you can hear me well. Yeah, okay. I was a member of WP2 for that project and was in charge of the coupled thermohydraulic modeling and simulation of horizontal ground loops. So without further ado, let's just start it. In this slide, a conceptual distributed heating and cooling network is illustrated. On this figure, we can see that the shallow ground is working as a heat sink and heat source. Therefore, the ground characteristics should be thoroughly studied for an accurate investigation of the performance of the network. There are 2 points to make. First, we should know the soil in the ground is multi-phase and multi-composition material and often in an unsaturated status, which comprise of solid particles, liquid water, and gaseous air and vapor. The thermophysical properties of soil depends on its composition. and phases. In geotechnical engineering, we often employ a three-phase system of soils, which is a simplified model to quantify soil properties and processes. The ratio of each phase in the model is identical to real soil. Second, if thermocouples are installed along the depths of the ground to measure the ground temperature, we can find the ground temperature varies with time and space as shown in the lower right figure. From this figure, we can observe that there's a threshold depth where the ground temperature basically keeps unchanged, and the threshold depth varies from region to region. In this slide, let's take the profile of shallow ground as example to help us to build the coupled thermohydronic model of the unsaturated ground, which is from the ground surface to around 10-meter depth in Earth. In the ground, flow of heat and moisture condition constitutes the two main processes: heat transport and the mechanism of convection each phase, and the latent heat of evaporation of moisture is also considered. A moisture flow within unsaturated soils can be described as a two-phase process comprising of both liquid and vapor flows. Based on the conservation of energy and mass, we can obtain two governing equations for heat and moisture transfer in the unsaturated soil ground. For the shallow ground, the ground atmosphere boundary is of significance where heat and moisture exchange occur constantly. Four major mechanisms of heat exchange between the ground surface and the atmosphere are considered. In addition, the ground moisture flux is affected by rainfall, evaporation, and runoff. Overall, there are 5 climatic variables need to be considered to model the ground surface boundary. With the installation of ground loops, another boundary is introduced to our model. We call it ground loop boundary. On the surface of the pipes, there are heat exchange between circulating fluids, pipe, and adjacent ground. Therefore, a coupled thermohydraulic model subject to complex ground surface and atmospheric boundary conditions and ground loop boundary condition is built, which can be used to predict the temperature and moisture distribution with and without heat extraction and injection. The corresponding outcome has been published in our paper in renewable energy. We conducted a case study based on an experiment site located on campus of the University of Warwick to investigate the thermal behavior of ground before and after the installation of horizontal ground loops. Based on the borehole data from BGS, the shallow ground is made of 3 layers of soils, and the corresponding soil parameters can be obtained from literature data. 200 U-tube pipes collected in parallel were designed to extract heat and or inject heat into the shallow ground to meet the size thermal demand. Taking one representative unit of the horizontal ground loop as an example, as shown in the right figure, a 3D model domain is built. As shown in the figure, the U-tube ground loop was buried 3 meters below the ground, and the length and spacing of the 2 legs of the ground loop were 200 meters and 1 meter respectively. On the domain surface, local climatic conditions were prescribed, and fixed temperature and saturation were assumed at the bottom of the domain. In addition, the thermal load from 3 buildings of the experiment site was prescribed on the ground loops. In the system, there was water was adopted as heat carrier fluid, and the inlet and outlet fluid temperature difference was fixed at 4 degrees Celsius. 2 representative locations of the depths of 3 meters were chosen, and they were adjacent to the inlet and outlet. For further information of this modeling, please refer to our paper published in Geosemics. In this slide, the result of undisturbed ground temperature, namely before the installation of horizontal ground loops, are shown. On the left, it shows the variation in undisturbed ground temperature with time at various depths. As can be seen from the figure, the amplitude of ground temperatures decreased with increase of the depth. Curve peaks will offset one another with back to depth. In addition to that, an annual periodic pattern can be observed in an undisturbed ground temperature after about 2 years. On the right, the variations in undisturbed ground temperature with depths at different days are illustrated. As mentioned, any ground temperature varies temporally and spatially. Based on the result, the January and February temperature curves define the lower bound of the temperature range, while the temperature curves in August and September determine the upper bound. In the following slide, the ground temperature at 2 representative locations and the inlet and outlet fluid temperature results under straight heating and cooling ratios are presented. As shown in the left figures, after installation of ground loops, the ground temperature declines significantly during the heating period in compared to the undisturbed ground temperature. And once the cooling mode was on, the ground temperature increased or even become higher than the undisturbed ground temperature. After about 2 years, an annual periodic pattern in the ground temperature can also be observed. The inlet and outlet fluid temperature on the right basically shows the similar changing pattern. So from the case study, there are 2 key points that can be made. First, the fact that the undisturbed ground temperature varies with time and depth should be considered in the utilization of shallow geothermal energy. Second, the coupled thermal hydronic model subject to complex soil and atmospheric boundary conditions and ground loop boundary conditions is proposed and can be applied for the utilization of shallow geothermal energy. Michael, please take it over.
Thanks, Fu. So the main thing that differentiates these balanced heating and cooling networks from conventional high temperature district heating is that you have warm and cool pipes rather than supply and return. So the buildings can either absorb heat from or reject heat to the network. And so we have bidirectional mass and energy flows between them. So the end user substations would need to be very different. You'd need decentralized pumps, which can reverse flow direction. And we need to have separate heating and cooling systems, which, if operating simultaneously, can interchange heat between one another. But the exact configuration of those heating and cooling systems will depend on the nominal pipe temperature in the network. Before looking more closely at substations, I just thought I'd show our 2 research questions that we wanted to answer. There seems to be a lot of variation in the literature regarding the nominal pipe temperature for these types of network, and also variation in terms of when heating and cooling networks are appropriate based on the heating to cooling load ratio. So we wanted to look at how both the levelized cost of heating and how both affect the levelized cost of heating and cooling. And this is a metric that takes into account the discounted costs for investment and operations over the system's lifetime. So when calculating this levelized cost, we obviously need a calculation, and this takes inputs such as equipment prices, maintenance costs, and electricity prices. We also need to know numbers of units of equipment, their capacities, and annual electrical consumption. And so to determine these things for a given set of parameters and annual profiles of building loads and climatic conditions, then we require the simulations that Wu and I are presenting today. So this slide is just to show where they fit together and the information that's exchanged between them. And I'm just going to go into a bit more detail about this substation network modeling for this simulation. So within the simulation, we have a number of base components such as heat pumps, chillers, heat exchangers, etc. And we can take these base components and configure them in various ways depending on how the nominal pipe temperature is controlled in the network. So, for example, if we had no control of nominal pipe temperature, meaning that it just varies with the temperature of the ground source, then the substation for the ground source would consist of just a simple pump and 3 port valves, which are used to direct water around the array and into either the warm or the cool pipe. If we want to fix the nominal temperature above that of the ground array, then we would need a heat pump to raise the temperature. And with that configuration, any heat rejection back to the ground can be achieved either through a bypass or by active cooling with the heat pump, depending on the relative temperatures between the ground and the network at the time. Similarly, for building substations, in the case of heating, if the nominal pipe temperature is lower than the supply temperature of the building, we need a heat pump. But if it's high enough, we can just use a heat exchanger for passive heat transfer. And for variable nominal pipe temperatures, it may be possible to passively cool buildings when temperatures allow. But we may need to retain the option of an active cooling as ground temperatures can change throughout the year. And the heating and cooling systems of the building substations will be modelled with one of these 3 configurations. And returning to the University of Warwick case study then, this is a diagram of part of their existing high temperature network. We've retained the topology from this network, which connects the main energy centre to 3 buildings, which are Scarman House and Lakeside 1 and 2. And we've replaced this network with balanced heating and cooling network with ground array, for which we assume the building heating loop supply and return temperatures of 50 and 30 degrees C, and for cooling 15 and 21 degrees C. Heating loads for the case study were those that are logged from actual data from these 3 buildings, and the cooling loads, as they don't actually currently have cooling, are estimates for Warwick in the year 2030 for educational residential buildings. We scaled these cooling loads to look at low, medium and high cooling scenarios in the next slide. For the study, we've considered these 4 configurations based on nominal pipe temperatures. So if we allow the temperature to vary with the ground, as in T-var, we can use passive equipment at the ground source substation, active equipment for building heating, and have the opportunity for using passive building cooling. Whereas if we have a high nominal temperature, as in T58, then we can have passive equipment for building heating, but need heat pumps installed at the ground substation and chillers for building cooling. And for the 2 intermediate configurations, we would require active heating or cooling equipment in all 3 areas. In this slide, we see WOO's early results as the solid lines, and those solid lines are for the T-var configuration with passive cooling, and the dashed lines are for the other configurations where active cooling was required. And this demonstrates the effect of active cooling on ground array temperatures, since more heat must be rejected to the ground than when rejecting heat at elevated temperatures. So there's a feedback loop here which we wouldn't have captured without running these 2 simulations side by side. Here we have the results for the levelized costs of heating and cooling. The maroon coloured bars are for heat pump and chiller operation, which is the biggest driver of costs. The capital costs for these are also significant, which is the yellow bars. The main point here is that the configurations with active cooling all perform worse in every scenario, and that the higher the temperature, the least robust it is against future increased cooling. We also see that not only does the T-var scenario demonstrate the most cost-effective option in heat-dominated scenarios, it also becomes more cost-effective as we keep adding the cooling loads. And just also to note that the pumping costs, though not a huge factor, which is F, the blue bars, light blue bars, they were the smallest for the T58 configuration, so less on hydraulic pumping. But what we'd like the takeaway point to be is not that this is exactly how these networks should be designed. The horizontal ground source array can be a sustainable ground source if you have sufficient land and suitable soil conditions. Varying nominal pipe temperature can be the most cost-effective choice, but we could have changed any number of parameters if the case study and got a different result. For example, if we had a different pipe topology with longer pipe lengths, or if there'd been better overlap between heating and cooling loads. But what we've hopefully shown is that we have these tools available to assess these networks on a case-by-case basis. And these methods are already published or are currently under review to be published, so they can be accessed in that way. And that's it from us. Thank you very much.
Mike and Wu, thank you very much indeed for that presentation.